Okay, let's start. Let's pick up where we left off. Last time we were in section 1.6, I think, which was logarithmic functions. We defined what a logarithm is, so let's just recall that. If I write log to the base a of b equals c, that's the same as me writing what?
A to the power of c equals b.
Okay. What if I write ln of b equals c? What am I saying?
Log of base e.
Are you telling me are you translating this?
Yeah.
I mean, give me an equivalent statement to that.
Oh.
Huh? The equivalent statement of this for this.
E to the power of c equals b.
Why was that so hard? Right? This just means a is replaced by e. That's basically it. Don't let it scare you. So, what does the graph look like? Y equals, say, ln x. Like this. Okay. Did you guys? How many people got that one on the quiz? Okay. What about? I think I put this one on.
Yeah.
What was the rule for that? What did that mean? Okay, you're right. Right, you can move that up. What about ln of x times y?
Take the y out.
Plus ln of y.
What do you mean take the y out? What's to take the y out? Okay. Okay. All right, so logs are just another way to rewrite exponential equations. Let's actually continue with that. Like, so yeah, those 10 rules you're gonna have to know that I mentioned, and you'll need to know those for the homework as well. Let's see, so we did the rules, the definitions, I talked about the graphs and that they were inverses. I want to mention something specifically. Piggybacking off the less important rules that I gave you guys, there are some things I want you to immediately know once you see them. For example, if you see ln of 1, or if you see ln of e to anything, or if you see e to the ln of anything, ln of 0, there's another typical rule that you should know. Oh, well, the other way. No, I didn't. Yeah. What are these? ln of 1.
Zero.
It's 0. Why is it 0?
Because it's kind of the result. It was like literally e to the power of something has to give me 0.
No. If that was true, there would be no answer. ln means the base is e. So if I say ln of 1, what am I saying? What do I want?
E to the power of something gives me 1.
Yeah.
Which in that case is 0.
0. Remember, log to the base a of 1 is always 0, no matter what a is, right? It's true for e as well. So ln of 1 is also 0. What about ln of e to the x? It's just x, right? Which, by the way, means that if you only have if you only have, say, ln of e, what would that be?
Just
X. Be 1.
It would be 1, right? So you can do it by that shortcut rule that I told you about log to the base a of a to the x is just x. Or you can just think of it, what power do I have to raise e to in order to get e to the x? Well, obviously x, right? If I raise e to the x power, I get e to the x power, right? What about e to the ln x? It's also x, right? This is going by the idea that these guys are inverses, which means if you plug one function into the other, they cancel each other out, right? So if I have ln and I plug in an e to the x, the ln and the e, you can kind of think of them as canceling. They're inverses, they're opposites. Similarly, if I plug in the ln into the e, you kind of think of them as canceling, and you're getting whatever is up here. Now this thing doesn't have to be an x, like whatever was there, right? So this was a 3 or an x squared plus 1, you just get that thing itself. What about ln of 0? What's that?
Undefined.
Undefined, because log of 0 is always undefined, regardless of the base. Same way that log of 1 is always 0, regardless of the base. As long as your base makes sense. Okay. So I just wanted to mention some of those things specifically. Because as you can see, sometimes students see ln and it's like their brain shuts down and they forget everything. Like the rules are exactly the same. There is no difference. Nothing has changed, right? Log to the base a, ln is the same thing. It's just that the base is e and they're not telling you, right? It's just the log, like any other log, right? Because above here I wrote, okay, so if I brought log to the base a of b equals c, what does that mean? A to the c equals b, I got that right away. Okay, if I write ln of b equals c, what does that mean? It's exactly the same. There's no difference. Do not be afraid of the notation. Okay. We have to get out of that habit of, oh, the math looking scary, so that means it's hard. That's not what it means, right? It means you think of it in the simpler way and just work your way through. Okay. So let's actually continue. I wanted to kind of start combining the last two sections, 1.6 and 1.5. And let's mix some exponentials and logarithms and start to see how they can work together, because we're going to need to solve equations involving both. So here are some examples. Simplify the following. E to the 5 and 2 log to the base 2 of 2 to the 5, c log to the base 2 of x minus log to the base 2 of x squared plus log to the base 2 of x to the 4th, d e to the ln x squared minus 5 ln y e ln of x squared minus 1 over x times x plus 2 squared. For this one, when I say simplify, I want you to simplify by combining. And for this one, I want you to simplify by expanding in the sum of simpler terms. Okay, let's start with A. E to the 5 ln 2, simplify.
So 2 to the 5th.
What? How'd you get that?
2 to the 5th.
2 to the 5th? How'd you get that? Like, what do you think?
Since you can put the 5 on top and then ln and e cancel.
Right, so you can put that 5 up here. How do you know that?
Because that's like a rule
What was the rule?
backwards. How you can bring the exponentials down.
Yeah, tell me the rule. How do we know that?
So it's like ln of x squared would be x log, 2 log x.
What's the general rule? Why is it just n ln of x equals ln of x to the n, right? In fact, it can be more general. Log to the base a of x, if you multiply by an n, is log to the base a of x to the n, right? That's how I know. I can move this up. Okay, now once that is up, what does that mean? My e and my ln are right beside each other. There, one is plugged into the other, so they kind of cancel. And I'm left with 2 to the 5th, which is 32. So that actually simplifies to 32. Another way is, if I had e to the 5 ln of 2, I could have thought of it this way. Right? Because that's the law of exponents, right? Since I know that if I have x to the a raised to the b, it's the same as x to the ab. So I could have done that. And then on the inside, the e's and the ln's cancel. That gives me a 2 to the 5th power. And so that would also be 32. So there are a couple ways to simplify that one. But this one's probably using the rules of the more straightforward one. Let's look at b. Two to the log to the base 2 of 2 to the 5. There's an easy way to think of it and a little bit harder way, but both of them. We'll get to the answer quickly. What's the answer? Huh? How do you get that?
Because your mom takes it 2 and 2 cancel. And then you get 3 to the 5th.
Yeah, so you can look at here, log to the base 2 of 2 to the 5th. That just cancels, that gives you a 5, which is 32. You could also just use directly that rule that says, if I have a log to the base a of x, that just gives me x, right? So you have 2 log to the base of 2, and this now represents my x, right? So you can see it that way as well. Right? Whichever way you see it, see it quickly. See. Should be almost like a knee-jerk reaction eventually. You should really be studying those rules. See, I said log to the base 2 of x minus log to the base 2 of x squared plus log to the base 2 of x to the 4th. Okay, rewrite that. Huh?
What do you mean? X over x squared times x to the 4th?
Log to the base 2 of x over x squared times x to the 4th, and all that's in the log.
Yeah.
Right? Because we're using here log of a sub. The difference of logs is just the division, right? So I put the x over the x2, and then I have that log added to another log, which means I just multiply the insides. So I end up with this. So ultimately, it simplifies to what? What does that simplify to? X cubed. Right? Or 3 log to the base 2 of x. That's also the same. D. This was similar to one of the quiz, I think. Simplify that. How'd you get that? Yeah, but we have 2 logs here. Okay, so how did you get that one? So you simplified the power. So you applied 2 rules at once, it seems. So you first took this 5 and moved it up, I guess. So you get ln of x squared minus ln of y to the 5th. And then you use that rule to combine those two, ln of x squared over y to the fifth, right? All that is in the log. And now this just goes. There are other ways you could do it. You could do something like this. More than one ways to skin a cat. You could again use the laws of exponents and realize that this is e to the ln of x squared times e to the minus 5 ln y. And this would kill that, and you'd have them multiply because of that product, right? Which is the same thing. Was that the last one? No. What about this one? We've got the D, E. ln of all that. Expand and simplify into simpler terms.
I think it has to do with one of those, like, finding the common base, some sort of, like, the common, it's, so it should be ln of x squared minus 1 to the power of 1/2 over, yeah, ln of x squared minus 1 to the power of 1/2 over ln x, in parentheses, x plus 2 squared.
Is that true? That's what you said. You said ln of this over ln of that. That's what you said, right?
Well, that and finding like a common.
No, you're thinking too hard. In fact, you do want to start by thinking of this, but that's not it. What is this?
You're supposed to subtract it, right?
What is that?
ln of a minus ln of b.
ln of a minus ln of b. Again, don't get distracted by how scary something looks. Think of it simple. This is an a, that's a b. Right? So what is that? ln of this minus ln of that. Okay, now continue. Yeah, Tiara?
1/2 ln x squared minus 1.
Okay, so here, this radical, she rewrote that as a power, and so she brought that power down because that's another root. Okay,
And then minus. Ln x plus 2 ln x.
he's skipping so many steps. You're not as smart as you, please. Okay, so that's one. Again, this is applying another rule. This is log of a times b, right? Which is a sum. Now she opened parentheses because she's subtracting, because that would be a minus, right? You wouldn't write a minus and a plus. It has to be in brackets. It's going to distribute. Okay, now what? Here. So here's what you said. You can bring that 2 down. Okay, can we go further? What's further? Is this as simple as it could be? What's x squared minus 1?
X plus 1.
What'd you say?
X plus 1 is minus 1.
This you can write as x plus 1 times x minus 1 minus ln x minus 2 ln of x plus 2. Okay? Equals? Equals what?
Well, would it be minus 2 ln? Wouldn't it be plus? Oh, I got you.
Parentheses, it would distribute. So what about this guy? Can't really do anything with that, that's ln x. That's pretty much as simple as it's going to get. This guy, can't do anything with that either, because that's ln of something plus something, which we don't have a rule for. What about this guy? Can that simplify?
Yeah, ln x plus 1, ln x minus 1.
No.
No, plus.
So you want me this ln of x plus 1 plus ln of x minus 1 minus ln minus 2 ln, like that?
Yeah. Yeah.
Yeah? Right. There should be parentheses, so technically there should be a half in front of this one as well. So one half ln of x plus 1 plus 1 half of ln of x minus 1 minus ln x minus 2 ln of x plus 1. X plus 2. Okay, and that's expanded into much simpler terms. Now, pretty soon, by the end of this week, will we finish that by the end of this week? We probably will. We're going to learn about differentiation, and we'll get to something called the quotient rule, where I might ask you to differentiate something that looks like this. When we get to the quotient rule, you're going to realize that that is insanely annoying. With an ln in front of it, though, it will break into this. And I'm going to give you another rule to differentiate things with ln of something. And you'd realize that each of these are insanely simple, right? So being able to go from this to that is going to actually help you out a lot. Let's see. Let's do some more. These should probably not be so bad. Solve the following equations. Ln of x equals 7. E to the 2x minus 7 equals 10. 3 equals 5 times e to 3x. 2 to the x squared plus 1 equals 5. Solve those as in solve for x. Tell me what x equals to. Solve for x. Ln of x equals 7. Order, don't everyone shout it out at once.
E to the 7.
Could you erase everything by e? So the ln would cancel and you get x equals e to the 7.
You could. You could also apply the definition of the log right away and just know that the base here is e. So that says e to that power gives me this number. Right? Or there's another idea of how people like to think about it. Well, this is equal to 7. You can put both of them in the power of e, and it should still be equal, right? That knowledge, you kind of have to know that e to the x is a one-to-one function, but I guess. And then here, the rule says this will cancel, and then that's just e to the 7. So that one's not so bad. It's actually a direct application of the definition. What about this one? E to the 2x minus 7 equals 10. So again, now we're using the fact that our exponentials and our logarithms, they're actually one-to-one function. They don't only pass the vertical line test, but they also pass the horizontal line test, which means they're special. Which means if the inputs are the same, the outputs are the same, and that allows us to do things like this. So here, notice that we knew that the exponential and the log are inverses, so what I know is that if I plug in a log into an exponential with the same base as the log, what will happen? It will cancel. Similarly, if I have an exponential and I want to get rid of the exponential, what am I going to do? Plug it into the log, right? The exponential will kill the log will kill the exponential, vice versa. So what we can do is, if this equals that, then if I take the log of this, it will equal the log of that, right? And the log I'm going to use is the one that has the same base as the one I want to cancel, right? So the x I want to solve for is in the power of the e. That e is in the way. I need to get rid of that e. How do I get rid of an e? ln gets rid of an e, right? The log will cancel the e. So this would cancel, and what would I be left with? 2x minus 7. So what's x? X would be? Ln of 10 plus 7 over 2. Okay. We don't have calculator, so you leave it as that. Like, you won't know what ln of 10 is. So that would be the answer. See, 3 equals 5 times e to the 3x. Solve for x. Okay, ideas?
Wait, is that?
What?
3 equals 3x cubed.
3 equals 3.
I mean,
ln of 3 equals 3x to the 5th. How did you get that?
well, first you count both sides.
Okay, so if I ln both sides, what's going to happen? Yeah, that 5 is not going to be in front. You could still salvage this, but I feel like it's you're making it harder than it has to be.
What do you divide the 5 off?
Huh?
Divide the 5 first.
Divide the 5 off, right? So notice that I need to get to that x, right? But the x is inside an e, right? So in order to get to the x, I need to get to that e, right? So if you had something like 3 equals 5x, what would you have done? You'd just divide off the 5. You'd do the same thing, right? First divide by the 5. Now I have the e on its own. At this point I would ln both sides. And then what would happen? ln and the e are going to kill each other, and then I'm going to have what?
3x.
3x. How do I solve for x? Divide by 3. That's going to be my x. This is the idea I want you guys to like have cemented in your minds. Think simply, right? When something looks scary, think of what it would be like if it was simpler, right? You have this e to the 3x, that's kind of scary, but what if it was just an x? You would have dealt with it differently, and you just continue that, and then you break it down until you get to parts where you can say, oh, that's just a rule right away. So we had d, which was 2 to the x squared plus 1 equals 5. Yes. By the way, before this, let's say I had 2 to the x squared plus 1 equals 2. Let's make it a little bit more interesting. 4. Let's work on this one first so that I can make a comment about that one. How would you have solved this one?
So 4 you can rewrite as 2 to the power of 2, and then if base is equal, you can set exponents to equal.
Right. And here again, you're using the fact that the exponential is a one-to-one function. So you just, if it's possible, right, you rewrite one side in terms of the base of the other side. Once the two bases are the same, the powers have to be the same, right? You equate the powers. And so you'll get x squared plus 1 equals 2, and so you would have x squared equals 1, so your x equals plus or minus 1. Right, now notice here, we can't actually do that, because we actually don't know how to write 5 as base 2. At least we didn't before. What do we do now? You can do log to the base 2 for both sides. Now what? What happens now? And we have x squared plus 1 equals log to the base 2 of 5, which means x squared equals log to the base 2 of 5 minus 1. So my x would be plus or minus the radical of this. How do I know that this makes sense? Or does it make sense? Is there even a solution? Because I know if I have a radical, what's the issue here? There can be a negative under the bottom. So is this a negative or a positive? What do you think? Why is it positive?
Just have to be bigger than 1. Which means x.
How do you know it's bigger than 1? What makes you think it's bigger than 1?
The number on the left just have to be bigger than 1. Which means that the log 2x just have to get bigger than 2. 5 is bigger than 2.
Yeah, because you know that log is an increasing function, right? So the smaller xi's would have smaller values. In other words, if I have log to the base 2 of 4, that would be less than log to the base 2 of 5, right? But I know log to the base 2 of 4 is actually 2, right? So this number here is bigger than 2. Don't know exactly what it is, but it's bigger than 2, right? In fact, it's going to be somewhere between 2 and 3. And so if I have 2 minus 1, that's positive, so I know that this will work out, right? So it does have a solution. All you have to do is just think of powers of 2. Think of the closest power of 2, the power of 2 that's closest to 5, and sort of use that to guesstimate it, to see if your answer actually makes sense. Right? You don't have calculators, so you kind of have to know how to guesstimate certain things. Yep, that's pretty much all we need for 1.6. Right? So we know what logs are, exponentials are, how to graph them. We'll actually come back and do a little bit more with these things when we get to the calculus of them. But for now, how to solve basic equations, how to apply the rules, how to know what the pictures look like, that's the important part for this section, I think. So with that, you should be able to do the homework, which is now due tomorrow. Yeah. Any questions on this topic? Anything that was confusing you?
So, like, let's say you have ln of e. Like, how does the ln and the e kill each other?
Like ln of e?
Yeah, literally. Like,
You think of ln of e to the 1. So then you ask the question, what power do I raise e to in order to get e to the 1? The answer is 1. You start thinking that's killing each other. They cancel each other.
so basically, if I had ln of e to whatever power, that would literally be the same whatever the power
Yeah.
was.
Yeah, so if I have ln of e to the pi, that's just pi. Right? If I have ln of e to the radical of x squared minus 1 plus pi cubed minus 4, you don't panic and freak out. That's the answer. Okay. We're going to move on to chapter 2, which means we're super close to actually doing some calculus. We haven't even started calculus yet. We're moving on to 2.1. I believe it's titled Measures of Change. There's really only one thing we need from this chapter. It's basically one formula.
Let me guess.
What?
Limit as h approaches infinity of f of x plus h minus f of x all over h.
No.
Okay.
That's almost what a derivative is, not quite. But that we don't get to till like 2.3. Yeah. So we're not there yet. Here we're going to talk about the average rate of change is the main thing I want to discuss in this section, which you'll notice that I actually asked you that as the bonus problem in the quiz. So here's a definition. Well, this is referring to how a function changes on average, right, or overall on some interval. Right, so if we're looking at our function here, let's say I have this random function. Let me make it look like something like that. No, it doesn't have to. And I'm like, okay, how did the function change on average on this interval, on the interval AB? Right? Right, what was the change in that function on that interval? This is f of x. Well, if my x value is a, the corresponding y value would be f of a. And if my x value is b, the corresponding y value will be
f of b.
f of b. So what's going to be the change in my function? The change in its value is just going to be this difference, right? But I want it with respect to some interval, over that interval. It's kind of like what I was mentioning about the slope. How we had that, the average rate of change of that car that covered 80 miles in 1 hour. On average, it had to be traveling at 80 miles an hour, right? So it's sort of that same idea. When you're talking about how this function changes on an average, you're basically going to get basically the slope. Right, so that leads us to our definition here. That's going to be a very important one. For a function f of x, the average rate of change of f on the interval AB is given by, and here's that formula which now you have to have memorized. So average rate of change is something you're going to be asked about all the time. F average is f of b minus f of a over b minus a, right? Which is basically the slope. It's kind of like you have your y2 and your y1 and your x1 and your x2. You find the slope, it's y2 minus y1 over x2 minus x1, right? That was how it's changing on average. That's your average rate of change of the function f. What's the average rate of change of that function on that particular interval? So of course, if someone asks you the average rate of change, they have to tell you where they're talking about. So you'll always be given an interval or some way to restrict your x values. So here, f average equals
I would assume 5 squared minus 2 squared on the numerator.
tell me the formula, what you're plugging in. Okay, so here our f of x is x squared.
Yeah.
So we want, let's just write out the formula first. F of 5 minus f of 2 over 5 minus 2. Now f of 5 is 5 squared minus 2 squared over 5 minus 2. So that's how you got that. And then what do you have here?
That'll be 25 minus 4 over 5 minus 2.
Is 3.
Yeah.
So that's
Okay, since you want to jump ahead, it's 7.
21 over 3 equals 7.
But, okay, so now we got 7. What exactly does that 7 tell us?
It tells us on average over this interval, the output values of x squared will change by 7.
7 as in the
7
slope?
units, as in, so we have y equals x squared. So this says here, this is 2. Here, this is 5. So this says here I would have 4. Here I would have 25. So it's basically talking about the slope of this line,
Ah.
right? So that's telling you how much your y value will increase per unit of input, right? So here I went through 3 units of input. How much does it increase per unit? Well, it will increase 7 times per unit, right? So I go from here to here, and it's going to increase by 7, then by 14, then by 21. Right, so it's telling you per unit of input, how is your output changing overall on this interval, right?
And I'm assuming that that average would be different if we were to play around with the interval.
Yeah, so if you went from 2 to 7, it'd be a completely different number, because now you're going from 4 to something higher. You want to know how much on average is that changing. per unit time or per unit something else. So you kind of want to think of it as a slope, how if you move over 1 unit here, how high are you going up, right? So it actually means you move up by 7. And by the way, there is an interpretation to the fact that this is positive 7. That's telling you that it's increasing. Of course, if your function was doing that, and you apply this formula, you'd have gotten negative. So that tells you per unit time, it's decreasing on average. And on average is important because your functions can actually be doing something crazy. They don't have to be like that. They could be like, right? So it could be like hard to follow, and you're just like, okay, on average, what's it doing? You know? Sometimes that's all you need. Like if you go from here to this point over here, on average, you're decreasing, right? So that's important, right? But try to figure out what the function is doing on the in-between can sometimes be hard to manage, hard to track, right? So sometimes you look at averages, right? So, you know, if you're dabbling in the stock market, you watch it every hour, you'll go crazy, right? But you just want to know at the end of the day, at the end of the month, at the end of the year, I'm actually making money. That's the important thing, right? So average is sort of looking on something over a wider time interval and knowing how it will work out on average overall, right? And that interpretation is just the slope connecting those 2 points. So that's what that's about. I could give a couple more examples, but I don't feel like it. Really interested to actually start calculus, so let's start calculus.
We're already done with 2.1?
No, that's literally the only formula you need to know. That whole chapter they were talking about that formula. What do you know homework? Tons of homework.
You gotta do 1.6.
Yes, limits. What calculus is all about, quite literally. So remember I was telling you about calculus was really the answer to 2 basic problems. There was the rate problem, figuring out how fast something is moving, and there was the area problem, figuring out how much space or area something takes up. Turns out these were inverse operations of each other. The tool that we use to study the rate problem is called the derivative. It's kind of a rate of change, how fast something is moving. The thing that we use to study the area problem is called the integral. Now it turns out both of these tools are actually defined in terms of limits. So really, whether you're studying derivatives or integrals, you're really studying limits. Calculus, in one word, is about limits. Right? Now what limits deal with, the idea here is to analyze, how can you say this, closeness or approach. That's kind of what limits are all about, right? When you're approaching something or you're getting close to something, what is actually going on? And that notion actually brings us into calculus, as we'll develop pretty soon. So let's talk about some examples before I start to get into the nitty-gritty of what a limit actually is. So let's say I have a function, let's say it's y equals 2 minus 2x. What does that look like, by the way?
The y-intercept is on positive 2, and it's a downward facing slope where you go down by 2, and yeah.
So what's that going to be? What that point? What's that point?
Okay, so
What's your
One.
question?
1. Right? Right. So when my y equals 0, my x will be 1. So that's our function. Now let me ask you a question. What happens to y when x gets close to 2? Let's say I actually get that question. Right, so now I'm over here, right? Like I'm at 2. And I see this question. What's happening to the y? How is the y decreasing? I'm at 2. I'm not moving, I'm stagnating. Well, I'm getting super close to 2.
Then y is going to get super close to 4. Negative, that is.
It's going to get super close to 4?
Well, it's going to get super close to negative 4.
Is that true? I mean, when my x is 2, what happens here?
Y equals -2.
Well, this means that my y would get closer and closer to 2 minus 2 times 2, right? This is -4, but you add 2. So my y value is actually getting close to -2, right? So here I'm saying, when my x value is getting close to 2, what's happening to the y value? Well, that y value is going to get close to -2, right? Now, I didn't really say I have to be at 2, right? But I want to get close to 2. And so you might be saying, well, what's the point of that? Well, things can get a little bit trickier. Let's say I said something like this. Let's look at, like, I'm analyzing y equals 1 over x. Let me write that in the middle. By the way, what does 1 over x look like? And what? Okay, now, let me ask you a question. Yes, that's 1 over x. That was on the quick. Here's a question. So let's ask some questions, right? What happens to y when x gets close to 0? Like this. Infinity. Expand our brains. Yeah, so what happens to y when my x gets close to 2?
Y gets close to 1/2.
It'll get close to 1/2, right? So if I'm at 2, my y value is going to be super close to 1/2, right? Now that's kind of obvious because the curve is right there. I can literally just plug in 2 and get 1/2, and I'm like, well, that's what it's going to go towards, right? What if I said 0?
Then it'll approach infinity. Why?
Y will approach infinity if I get close to 0?
Because
Well,
you
from which side are you approaching 0?
Oh, that's a good question. So what can I say if I'm getting close to 0? What is my y value approaching?
No, from which side are you approaching? From the negative or from the positive?
No, in general, I'm getting close to 0. Is there an answer for what number I'm going to? Well, if I get close to 0 from this side, my graph is shooting up. If I'm getting close to 0 from this side, my graph is shooting down. They're obviously very different things, right? So here it's like plus infinity, minus infinity. We're going to define that. We're going to talk about that later. What about as x approaches infinity? By the way, what do I mean to approach infinity? What does that even mean? How does that make sense?
It means each biggest number you can think of, there's always like another bigger number.
Yeah, so as x approach to infinity, I'm kind of saying far to the right. Right? It gets very large. Right? So now as my x is getting very large, it's going all the way to the right. Farther than, when you think it's far, go farther. Right? Does my y value get close to something? Okay. So here, y would approach 1/2. Here, y approaches nothing, right? It kind of approaches, well, it depends on what side you're coming from. So there's not really an answer. There are kind of two answers there. We'll have to deal with that separately. But what about as it approach infinity, y would approach
0.
0, right? As my x is getting larger and larger, my y is getting close to 0, 0. It's getting super close to 0. Of course, it'll never actually hit 0 because the numerator is 1, but it's getting super close to 0. Right? Now, all these values in between, like sure it hits all these other values, but those don't really matter. I'm thinking about as I'm moving off far to the right? So there's this idea of approaching something, approaching infinity, or approaching a random number and looking at what your function is doing. Right? That idea is sort of what we want to capture when we're talking about limits, right? When we're approaching something, what happens to it. Now, if our function is continuous, which is something I'll define later as well, it's kind of easy to see it, right? But if your function has trouble, like there are asymptotes, or there are gaps, or there are jumps, it can get a lot more interesting. And you don't really know what the hell is going on, but we're going to have to make it very concrete. So that's kind of what limits are about, and we're going to expand on that idea. So let's talk about a definition. So basically it's talking about the behavior of our function based on the input, right? So I'm figuring out, when I'm tweaking the input in some way, what happens to the output, right? I could, is there any value in giving another example? Probably. Let's look at a couple more examples. Let's look at a function like this. Or let's say it's given by the graph. Sort of similar idea to what we had before, but let's or let my y be this function. Here I want x to approach 1. Here I want x to approach -2. Okay, what about this one? What does y approach in this case? As my x is getting close to 1, my x value.
From which side?
Analyze it. We're going from the left. Where are we going to? So if we're going from the left and my x value is getting close to 1, my corresponding y value is, it's also 1. So is the answer 1? The fact that it's open actually doesn't matter, right? I never said x equals 1. I'm saying it's getting close to 1, right? So as it's approaching 1, getting super close to that, what is the y value getting close to, right? But the thing is, this is only a part of my function. I have another part over here. Now if I'm getting close to 1 from this side, what's the answer? It's 3. So is it 1 or is it 3? It's both. How can you be both 1 and 3? 1 is not the same as 3.
Not quite. You're technically not quite 1, and you're likewise not quite at 3. But meanwhile, if you were at x equals 1 and you did the vertical line test, then your value would be 3, and it would be 3 and 1.
Sure, that's if I'm at x equals 1, but I'm not there yet, right? So it's kind of getting fuzzy, but we're gonna make it concrete. I just want you guys to start thinking about this idea, how you look at it. What about this one? First of all, I want you to understand why such an answer might be unsatisfactory, right? So, let's make it a little bit crazier. instead of 3, I have 1,000,000. I just want you guys to start thinking about these numbers in terms of other contexts and what this function could actually mean. Okay, so I'm starting, let's say I'm starting a certain business venture, and after analyzing things for a few months, I'm starting to analyze, the cost of something, and I realize, the company is losing money, and I sort of start tracking this over time. There's a certain time where something crazy happens, and it's not exactly clear what's going on. But anyway, this function would represent, how much money I'm losing, for example. And let's say I'm using this function to predict, like, how much money am I going to lose in the future if I approach some bad situation, right? So I can say, okay, over the past 3 Christmases, 1 represents Christmas, right? And this was kind of how things were going, right? So now I want to predict for the future Christmas, right? And I have nothing to go on but the data I have from before. So now I ask someone to, I ask a mathematician to kind of, have a function, talk about, revenue and analyze everything, right? And so he came up with a function like this. And so now I ask him, okay, so next Christmas, right, how much money am I going to lose, right? Now, if he tells me, well, you could lose $1 or you could lose $1,000,000, do you think I'd be happy with that answer? Right, it's not satisfactory to have 2 different answers in some sense, right? So if I say when x gets close to something, I'm asking what's happening to the y, I'd like a definite, definitive answer. I'd like something to be able to go up, something to be able to predict, right? Otherwise, it's not satisfactory. It's not essentially meaningful to me. It's not something that you can plan on, right? So that's one thing I just want you to kind of get when you're going with this. What about a function like this? What happens if I plug in x equals -2?
Well, you're going to hit another asymptote.
Are you? What happens when x is -2?
Undefined.
It's undefined. I divide by 0, right? So you can plug in x equals -2, and we know that we can plug in -2. But what if we get close to -2? Let's not quite plug in -2, right? Let's see what's going on when we sort of tiptoe to the edge of the abyss, right? So we know we can't plug in -2, but let's say someone says, oh, just get close to it, see what's going on. Just look over the edge. Don't do it because you'll get a 0. But what's going on with this function, right? How does it behave when you get close to -2? Well, what do you think? If I get close to -2, what do you think is going to happen? Any guesses? Am I going to shoot off to infinity? Negative infinity? It's going to get close to 0. It's going to get close to, what's going to happen? What's going to happen? What's going to happen? Any guesses? You think it's going to get close to 0? So if I plug in, say, close to 2, you might see something like -1.99999, right? Or -2.0000, right? You're getting super close to 2, and you're kind of trying to zone into what will happen. What do you think will happen close to 0? How about this? Now I know I can't be at -2, that's impossible. So let's make the assumption that our x cannot be -2. What's another way I can look at this function? We try to simplify, right? I gave you a similar problem like this in the quiz, to simplify something. How would you simplify?
X plus 2, x minus 2.
This is the difference of squares. I can do x plus 2, x minus 2, over x plus 2. Now what happens?
The x plus 2's cancel, provided that the... Yeah.
Right, provided that this is not 0, which I'm assuming it's not. It's nothing crazy. It's just one number times another number divided by that number. I can cancel. And so now this guy, he kind of behaves like this guy, right? So what's going to happen? What's that graph, though? What does y equals x minus 2 look like? -4. It looks like -4. The graph. What does that line, that graph look like? It's a line.
Linear lines, positive, and the y-intercept number 2.
The y-intercept is -2, and
The slope is positive.
the slope is positive. It's -2, slope is positive, so it's going up like this. And I'm asking you what's going on around -2. Now, what's actually going on around -2? Nothing. It's undefined at -2. There's a hole there, right? So now what can you say about this graph? As long as we're not at -2, this guy cancels, it behaves like this guy. And so I kind of behave like this line the whole time. So when my x is getting close to -2, even though I'm not actually plugging it in, my y value is getting close to something else. And what do you think that is? Well, I can use this function to judge this function when I'm not plugging in 0 in the denominator. And if my x gets close to -2 here, what's going to happen to the guy over here? What would that y value be if I could plug it in? -4, right? So it doesn't get close to 0. Doesn't get close to 4, doesn't go to infinity, doesn't go to -infinity. In fact, if my x gets close to -2, this expression gets close to -4. Right? And being able to say that is insanely important. You won't realize how important it is. I didn't realize the time was getting away from me. I broke my watch, so I don't. Didn't realize how much time passed. But that idea of being able to approach something that might not make sense to actually be there, but knowing what happens when you get close to there is a really powerful thing. And that's what we're going to use to develop the derivative next time. So I didn't even really start this topic yet. I was just sort of playing around with this idea. So next time we'll define limits, not in detail, but as detailed as you need to know in Tool 5. And we'll start to apply it to more calculus. Derivative. So homework, I wanted to answer a homework question, so we'll actually leave that for tomorrow. So keep your homeworks, we'll answer questions on them tomorrow. And the homeworks for the sections that I completed, they're actually due tomorrow as well. So we completed 1.6. So homework for 1.6 and 2.1 are due tomorrow. And I'll see you guys.